So, right, thank you, Maggie, for having a very nice introduction to the idea of folding. And I think my talk will be quite a nice continuation of that not very technical talk in the practical kind of applications. So my talk will be on proof recursion in practical zero-knowledge machine learning. And so here's a rundown where I'll start with kind of introducing the basic concept. If you already know what zero-knowledge machine learning is, you will probably find it a little boring, and I apologize in advance. And then we'll get into the more interesting things, which is folding, and how to use the folding scheme that Maggie has just introduced in zero-knowledge machine learning. And then we'll talk a little bit of like outlook of what's kind of the future after knowing all this folding, IVC, and how it's used in zero-knowledge machine learning. How else would we use it, or what's the future looks like? Right. So first of all, introduction. If you have read the recent ZK validator report, you probably see this on, I think, the second page or third page, which is a diagram that shows us how to, what the ZKML means. Right? And essentially we're talking about well, at least for nowadays, when we talk about ZKML, we're saying that there's some circuit in the middle, that performs neural network operations. Right? So neural network is everything that we know that's powerful in AI nowadays. And then we'll have some input data and model weights that goes into the circuit and predicts some outputs. And the problem with this diagram is that it refers to a single inference only, right? So that means that you put in one prompt into Stable Diffusion and it outputs an image, one single image. Or you put in one sentence into GPT and it outputs one single response. Which the problem is that's not how we usually use machine learning in most of the fields. Right? That's not how typically machine learning works. Because usually we have thousands and thousands of samples inside a data set, and we want to run the same model over all of them. And ideally, we also want to put them into the same proof, so that we're not submitting 1,000 proofs and the guess fee kind of accumulates like crazy. Right? And so
One question. Zero-knowledge means privacy, right?
Not necessarily.
Well, because that's the question I have. If you go back to the previous slide, which things are private and which are not?
Good question. So usually when I do a more ZKML focused talk, I will also demonstrate like what's going to be private or public. So here you have three options. You can have everything as public on the left-hand side, and that just means it's a validity proof or a rollup, right? So I want to do something in ML that doesn't fit in a smart contract, and I just want to prove that I've done it. So you could have everything public. But you also can have the option to keep one of the input signals, one of the two types of input signals private and have different use cases. So you can keep the input private for maybe, I want to show that I'm very good at generating some very nice AI-generated art, but I don't want you to know my secret. Or you want to, for a company, they will probably want to keep the model weights private, or hashed at least, like committed. But yeah, but here, in, at least for this talk, we're not concerned about, like, it will apply to any of the use cases, of the three use cases that I mentioned just now. So yeah, so this part of whether it's public or private is up to you, up to the use case. Right, so I hope that answers your questions. Right, so back to the problem where we want to do inference on thousands and thousands of samples. So we also want to prove something all at a time to save some gas fee. And hence, recursive proofs should solve the problem, right? Like at least from what Maggie just told us, it seems like a lot of the things should apply in this case. If we have 1,000 model inferences that we want to do, just have 1,000 IVC and then aggregate them or fold them together, right? And here comes like kind of what I've been doing on researching on folding in ZKML. And also just kind of like laying some of the challenges, what is being explored right now. And really the talk is mostly for getting people interested in this kind of area and like explore the future directions together. Right, so this is from a previous example that's not done by me, but done by another group. And the project is called ZKML, which stands for alligator. So the idea is they apply folding onto the machine learning model itself. So let's say you have some neural network. Basically what they have done is, for every single layer in the middle here, which is what they call the backbone, it's the exact same structure as in like a neural network. So the input dimension and the output dimension is the exact same like convolutional layer in the between. Right? So then using Nova, because they are all the same circuit, you can fold into one relaxed CS instance, and then you can compress this with basically the size of O1. So this is kind of the first application of folding in ZKML, and it's incredible because you can get a very, very deep neural network into a very small proof. Well, but there's a problem, because especially I came from a machine learning and data science background, immediately we found that it might not be very practical, at least if we want high-performing models. Right? So the idea of machine learning or AI is to actually extract signals from large dimensional data. So we actually want the dimension usually from this image to go down all the way until we get some classification. Right? But if we're folding the model directly, then these structures here has to be exactly the same. Meaning the dimensions of the data that goes through your model doesn't really go down until probably after the folding. Then at the end, you would like boil it down. So while this is incredible, because I think they got like 500 layers of convolutional layers into the same model and have a very small proof size, the problem is it's not exactly practical in the Web 2 sense where we want to get a very nice performing model onto ZKML. So, well, the idea is, well, why don't we explore folding on the other dimension, right? Because just now we're folding on the model dimension. How about we fold on many kind of model inference dimension, which is what I have done, is folding back inferences, right? So if you're doing one model performing 1,000 times, why don't we fold them all up? And here are some kind of documents if you want to look at like a more documented way. But the idea is that it's different from the previous example of Sager, right? Because Sager, you don't really need to access the intermediate state. I only want kind of the output state of all the recurrent layers until the end and get that result. However, if we want to fold back inferences, I actually want the result from every single inference in between. And that's not something that folding would give us, right? With folding, you only get the first input and the last output. So the immediate default thought is, well, we need to do some state management or data management. And I don't really have a definite answer, even after my research, like what should we do with all the state management? But just to kind of showcase, like, why is it not just like, okay, instinctively we can apply folding to machine learning and be done with it. So there's actually quite some interesting things of like trying to manage the state, trying to have all the data available to all of us. Right, so inclusion proof wouldn't work because inclusion proof, you can essentially just prove the 1,000 proof on the same thing, right? Because inclusion specifically doesn't tell you which index it is. So if you use a Merkle tree to kind of have a state management of all the data that you have, essentially we will have to do a Merkle insertion at every step, right? So we start from the zero tree and the zero roots in the beginning of our folding process. At each step, we insert the result into this zero Merkle tree, and then we update the roots, and then we get a single root, right? So again, the essence is that with IVC, with folding, the input dimension and the output dimension has to be the same. So either I keep a huge array, or I have to keep some single number that represents all my data. And here, with a Merkle root, you're able to do that. And of course, that means that it's cheap to prove individually on chain, relatively, right? But it's very expensive when you do it inside the circuit, if you're inserting every single step. And also, it actually doesn't solve the problem where we are not accessing the data itself directly in the proof. Like we're just having a Merkle tree, meaning that the data still somehow has to be stored off-chain somewhere where we can verify the roots. So that's the first attempt. The second attempt also didn't really solve the problem that I had, but just to showcase kind of another way of thinking so, is to, well, why don't we just hash the result with the previous results, right? So I get output one, put it into the next step, get the result and hash it again, and hash it again. So that's what's called recursive hash. Again, there are two problems with this, which is, well, definitely if we're just doing a hash, like a single hash operation at the end of each step, it's less constrained, so it's cheaper in terms of a CK proof. Now, the problem, however, contrasting with Merkle tree is that we cannot prove inclusion individually, right? So I can't just prove a single data is included in in this recursive hash that I computed. Okay, so this is kind of the two attempts that I've done. Again, no definite answer as to how we should do this state management. There is actually another project called Moon that is done by my PSE colleagues that allows you to also access the intermediate witness at each step. The problem with that, again, is that you're increasing the proof size. Right? So there are many trade-offs that you're trying to do when you're trying to get that data available at the end of this IVC, this whole folding process, but at the same time to kind of keep the CK proof small. Right, so just on another note is that typically at this point I'll get some question, which is, well, machine learning is very repetitive, so we can fold everything, right? For example, in a convolutional network, what the convolutional layer does is you have a huge image and you're applying the same convolutional filter onto different parts of the image, right? So why don't we fold that? If we fold that, isn't that gonna help us a lot with machine learning? And the answer is, again, it's not that simple. Right, so this is just what convolution means, and to be suitable for folding, or is it, right? So I don't have the benchmark result on these slides, I think, because they're just numbers. But essentially, it's not as easy as we thought for the same reason why it's not as easy for the batch inference as we thought. Again, it's a state management thing, right? If I do one matrix multiplication and I get one number, fine. However, if I want to do it in machine learning, not just that I need to get a number, I also need to tell the circuit where to put this result. Right? I want it to be specifically outputting at a location. And that actually increased a ON order of constraints where I need to have a bunch of switchers or selectors to specifically put the number onto that specific location that I want. Right? So again, it's not that simple, although at a big scale, you do get speed up using folding over just a naive approach. But the speed up is not that significant that it's like very worthwhile that everyone should do it like right now. But that's the idea. Right, so some of the current challenge is, well, for the second point for data availability and state management, I kind of already summarized it. And I guess the other thing that is also summarized in Maggie's table at the end of the first half was that, well, at least the current folding implementation is only done on Nova, and Nova only works on R1CS, which typically means that we will write a circum circuit, compile it down to R1CS system, or you can write R1CS directly. But that's what it works on right now. However, in machine learning, we kind of extensively use lookup a lot. In CK machine learning, we use lookup a lot because of all the nonlinear operations that we have. So that's currently not able to be folded, kind of. Right? So a lot of these, like, sigmoid function, hyperbolic tension function, we can't really implement it efficiently in R1CS right now, and hence they're not being folded, and that's also a huge trouble. Of course, that being said, there's a lot of other implementations that is done on all the other schemes that Maggie has mentioned, like Protostar, Hybernova, Sangria. So once we have that, we will be able to fold zero-knowledge machine learning much more efficiently. Right, so for the outlook, so here is a diagram from a implementation of using Nova over Circum circuits. And this is a diagram showing just how it works. It looks like every single other circuit that you have seen from Phonemic just now. I want to show this to you because I want to compare and contrast it with another thing that is very well known with machine learning, which is recurrent neural network. So recurrent neural network at some point was a big hit until convolutional neural network comes along. And then we realized that convolutional neural network is way too powerful, and we kind of forgot about this. Well, it's actually not that old, but okay, historical architecture. But once we think about folding, and if you look at this two diagram, recurrent neural network is exactly what we would do in folding or IVC. And hence, if there are some applications or use cases that would really have great machine learning performance with recurrent neural network, then you can apply it on and essentially get a very small proof. Right? So some of the recurrent neural network use case that I can think of is, for example, price prediction. Right? So if we have some time series forecast, you can apply price prediction. You can use a recurrent neural network and try to model price prediction. The second thing is actually trading bots. Right? So especially there's CPU coprocessor where you can access prices on chain right now. So access historical block data on chain right now. That means that you can essentially also prove the data that goes into your machine learning model. Right? So previously you might have to trust the data source. But nowadays there's CPU coprocessor so that you can have price that you can access on chain and then use it to prove that these are the data that goes into your machine learning model or your recurrent neural network. Right? And also, because I didn't really know about that until I started researching on recurrent neural network, but in the machine learning world, people are very excited about a specific class of models that's called RWKV. It's a recurrent network that performs as well as GPT-3. So they were able to get a large language model in a recurrent form without any they have a transformer-like architecture, but without any attention mechanism. If you don't know what that means, that doesn't really matter. But the idea is people are very excited in the machine learning world about these kind of new architectures because it saves virtual RAM. And that turns out to be incredibly important for ZK. Because right now we are also running into the same problem where if you have a large model, it doesn't really fit onto your machine's memory. So a lot of the weird optimization that the machine learning people does it for different reasons turns out to be incredibly useful for ZK as well. And that's kind of like another direction that is worth looking into. Right, or just a last word, or maybe we can go back to basics. So without even talking about folding or recursive proof, there's actually an idea that is from the EZKL team or C-conduit team, that, well, why don't we just try to have a method prover that chain proves, right? So we know hash works perfectly hiding the output or something. Why don't we just break down huge circuits into smaller circuits and have the output hash and just have a method prover proving that the hash output of the previous circuit is indeed the hash input of the next circuit. Right, so that is like the most basic idea of divide and conquer. And that is something that apparently no one has gone into somehow, but it could be kind of the lowest hanging fruit or the easiest way to get big circuits onto the chain. It doesn't have to be ZKML specifically, but of course, ZKML is currently one of the largest, like some of the largest circuits that we get, and that would be incredibly helpful to just have like some kind of chaining or method prover. Right, so with that, that marks the end of my presentation. And if you want to access the slides from today, this is my link tree. There are 3 different slides that I use in Paris. This one is the one that says recursive proof in practical ZKML. And if there's any questions for Maggie or me, you're welcome to ask. Thank you.